Okay, thank you.
Okay, the next talk is by Tilak Ratnanather from Johns Hopkins University. 3 normal coordinate systems for the cortex. Applications in the deafened courses of babies, adults, and cats.
I would like to thank the organizer and INI on the workshop organizer and the NSF that supported the workshop. I'm going to be talking about the cortex. I mean, people have talked about the hippocampus and a few other structures this week, but we specifically focus on the cortex. I will applicate in the deaf cortex in baby, adult, and cat. Did it work and collaborate with many people. 2 postdocs, Sylvain Arguillère, who developed the computational optimization algorithm and the theoretical collaboration with Laurent Younes, who developed the mathematical framework for this, and Kwame Kutten, who implemented all the application. And then my collaborator, Andrej Kral, Hubka, who worked with the deaf cat in Hanover Medical School. And then Michael Miller, who developed the whole mathematical framework of computational anatomy. The work is done and funded by computational neuroscience grant from MIT, National Institute for Deafness and Communication Disorder. Okay. With due respect to Stephen Hawking, I would have to say that the brain is the most complex organ in the universe. It's highly folded in a confined space in high order mammal. For example, the barrel is very smooth and not folded, but the mammal is highly folded. That's because you have optimized expansion in a confined space. You want to maximize surface area to be able to do all the kind of function like walkie, thinky, righty, what have you. Although the surface, the brain surface has to fold to accommodate this expansion and increase the surface area. But the most important thing to point is that volume is the product of surface area times thickness. Surface area is not influence of the gene and may have implications for schizophrenia and other kinds of mental health. Thickness is the influence of the environment, loss of hearing loss, eye diameter, and what have you. So the 2 important measures. Most people measure volume, but they fail to break this down to surface area and thickness, and I believe we should measure these 2 independently. Okay, in the brain here, with the multi-scale view of the brain, here we have this brain, at the coronal view of the brain here, at the cut in that view. And then you take a cut across here, you have the white matter, and then you have the gray matter, which is highly folded. And we have focused on cortical thickness with the distance between the inner surface and the outer surface. And then across the gray matter you have 6 layers. Layer 6 to layer 1. And then the gray matter and the white matter and CSF. And the macroscopically from an MRI scan you see 3 tissues, white matter, gray matter and CSF. Gray matter is what we were focused on. And the sensory cortex, auditory cortex is about 3 millimeters thick, and then the motor cortex is about thicker, and the visual cortex 6 millimeters. The 6th layer was discovered in the 1880s by a famous Spanish neuroscientist, and then we have the layer going, we have neuron going from the white matter to the top, the CSF. And these form orthogonal structure called cortical column, the functional unit of the brain. And they were discovered at Johns Hopkins in 1990 by Bernard Mouse-Castle, who won the Nobel Prize for this. The cortical columns are the functional units of the brain. You can see the column, and then layer 1, 2, and 3, 4, 5, and 6 are the functional units. They're about 30 to 80 microns wide apart. And they come from the Blue Brain Project at EPF Lausanne. So columns are formed by neurons migrating orthogonally through the cortical plate. Now, in the cortical plate, in the embryo, the cortical plate is a flat horizontal structure, and when in the embryo, the neuron begin to migrate orthogonally and then the brain begin to fold, and the column begin to form orthogonally, and you can see the vertical line, and the 1 year old human post-mortem, 3-year-old human, 5-year-old human, and 12-year-old human, and the auditory cortex, necessarily, and you can see the layer 1, 2, 3, 4, 5, 6. So it's very important to consider the cortex as a collection or column orthogonal to the white matter from the top to the bottom. The brain, the human brain, recently, last year, David Benson of Washington University, he found that the brain is composed of 360 different cortical regions. For example, the motor cortex, the auditory cortex here, the visual cortex, the prefrontal cortex, and they can be divided in many sub-regions. And at the macroscopic level here, in the microscopic level here, when we take a cut through the histological section here, let's say B comes from this wall of the first side of the area 46 in the monkey brain. That's an example of the monkey brain. And this is the cut. B is the cut of one wall, and C is the cut here, and D is the cut here. And different parts of the brain have different cellular properties. For example, area 12 will have different properties from area 46, and area 46 will have different properties from area 9 in D. So that area 46, the area 9, and the area 12. Okay. Different parts of the brain have different thicknesses. Let's look at this example from post-mortem study from Von Kahneman and Kutten in 1925, which is summarized by Karl Delius from Germany. Area 4 and Area 8, these are 5 different parts of the human brain. Area 42 or 41 and 43 is the auditory cortex. And they're 200 microns thick. And layer 6 is 1250 microns thick. And the total sum is 3850. Area 18, 20, 137. Area the human brain is about 2.9 millimeters. So different parts of the brain have different thicknesses. In 1929, Bach, a German biologist, he wrote this paper. Then in 1959, he translated the book, the paper into English, was formed as chapter 2 of his book. And he had a hypothesis that the volume preservation is there between adjacent areas. For example, if that in one area and in another area, he said that the upper layer, the volume of the upper layer is preserved as you go from one area to another area. Here, the volume of this area is the same as the volume here, and the volume of this area is the same as here. And he claimed that the volume fraction of a segment is constant across the whole layer, and the thickness of the layer changes to compensate for the curvature of the brain. And located at high curvature, the layer is relatively thick here, and located at low curvature is comparably thin. And he believed that this is true throughout the whole brain, and it's very influenced by curvature of the brain. And he was the first to propose Gaussian coordinates for the cortex, in which he proposed a coordinate system based on Gaussian coordinates, and in which you can it took about 60 16 years until we got MRI scan to how to convert this idea into mathematics. Okay, so I'll explain why we are looking at the auditory path or cortex. Okay, here we have sound coming into the cochlea, and then the pathway goes to the cochlear nuclei, and then up the brain stem to the thalamus, which is the gateway to the whole brain. And then from the thalamus, the activity goes to the auditory cortex. So, for the most part, that not come from Dama hair cells in the cochlea. So we don't have Dama hair cells that have limited auditory transmission from the cochlea to the brain. More recently, somebody has discovered that you can have Dama synapses in the auditory nerve because of loud noise. So be careful when you listen to loud noise and music. And so you can have Dama in the other auditory nerve, which can cause damage to the auditory cortex. So what they reduce stimulation in the auditory nerve with the consequence of deafness, and then you have consequently reduced metabolism, which means atrophy at each stage of the auditory pathway, cochlear, brainstem, thalamus, and auditory cortex. Here is an example of the connection between the nerve connection. Here is the normal density of connection in the auditory nerve, in the brainstem. Here, the lack of stimulus, lack of metabolism, it's connected a very sparse, which is why when you see people with cochlear implant, they begin to come from that stage. They get the connection become more dense with increased activity with cochlear implant. Okay, so we are going to be focused on the three major regions of the auditory cortex. The heterozoa, with the view of the brain looking this way, and so this is the heterozoa from the midplane of the brain to the side, and it contains the auditory cortex here, and here we have the secondary auditory cortex with the planum temporalis, which is where spoken language and which is spoken language meet. Important the language processes here. Those two regions are we're going to be looking at later on. And Deck and Cat, my colleague in Hanover, have been looking in the effect of deafness on the shape of the auditory cortex. Here is an example. Here is a normal cat, a cat called a normal cat, and you can see the auditory cortex at the deep and thin, where the dead cat is not so folded, it's thick and fat. So they're abnormality in the primary and secondary auditory area. And the normal hairy cat is deep and thin and folded, and then the congenitally dead cat is shallow and thick. The thickness and the curvature is affected by poor innervation of the auditory signal. Okay, so in the human, it's important to be able to the people have measured functional activity in the brain by looking at electrical recording of response to high frequency speech sound, ba and da, and by looking at the waveform of the whole response of the whole brain. You can see a waveform P1. It's a very important biomarker in the brain, and also N1, the second important biomarker. And this is in normal development. In normal development, P1, we measure the latency from 0 to the first peak, and also measure the latency from 0 to N1. So what we do in normal population, we found that the latency is very high in normal people, normal baby from 0 to 3, and then after 3 years old, it mature with the narrow band here. The narrow band is the maturation of the P1 latency type. Now, if you were born there and not exposed to acoustic stimuli here, three things can happen. If you get a cochlear implant before age 3, you begin to the latency begin to reduce dramatically and do that normal band work. Which means that before age 3, if you got a cochlear implant or diagnosed before diagnosed and get implanted, you can hear and develop normal and spoken language. And I see that the case now. After age 3 to 6, it works either way. You can be lucky, because it's sort of a hit and miss. Some people go into that narrow band, other people don't. But after 6, for the most part, you never get that normal bandwidth, and you get a polyphasic response, which is why it's very important to be diagnosed. We might rehabilitate immediately, either with herniate or cochlear implant. And at least the heterodyal at the planet table are structural correlates of P1 and N1. And N1 appeared in adolescence. We never found that N1 in doctors who never used hearing aids. And I was quite lucky to have N1 when I was small. Okay, so now back to thicknesses. There are many methods of computing thicknesses. Image-based or surface-based, they require a precise delineation of the outer boundary. And free surface are widely used software for cortical surface analysis developed by Bruce Fisher at MIT. And what he does, he embraces the inner surface towards the outer boundary. And he used a hybrid outdoor distance, which I will demonstrate later for thickness. And more recently, based on an idea by Jones, you assume that the cortex is a three-dimensional orthogonal grid folded orthogonal grid, and people can use it for image data or surface data. And this offers a natural notion of cortical depth. And more recently, diffeomorphic registration based by the group from the University of Pennsylvania, in which they image data, in which they map from white matter to an image matter white matter to a mask of white matter and grey matter, and you map the white matter to the outer mask, and you generate the thickness line. However, the main problem are conflicting results produced by different methods for similar data sets, and they are attributed inability to handle deeply buried first time. So I want to emphasize that morphometry is that more than volume. Volume, the area of the grey-white matter here, would reflect the connectivity between different structures in the brain, and laminar thickness of the cortex, of the grey matter, would reflect the activity of the cortex in the world. So laminar thickness is the sum of the thickness of the cortical area here. And we will focus on cortical area, specific cortical area, auditory cortex, visual cortex, but we do it separately. And we triangulate the outer and inner surfaces. And we use geometric approach rather than image-based, and we reflect a really thick representation of the cortex. What are the assumptions we want to make? Let's go back to the idea of cortical column. Okay. In my opinion, cortical columns are the functional unit of the brain. So the inner and outer surface respectively associated with the base and the apex of the cortical column. So we have the base of the inner surface. We have the cortical column. The cortical column goes from the base of the cortex to the top of the apex of the cortex column. And that they form a natural parameterization of surfaces. The base form the natural parameterization of the inner surface. The apex of the column form a natural parameterization of the outer surface. So I claim that nature has endowed the cortical area with a diffeomorphism from the inner surface to the outer one. In other words, we carry a map from one coordinate chart to another coordinate chart. The associated vector field get at the representative column, and then we impose constraint. We compose the constraint that at the base of the column they're orthogonal, and at the top of the outer surface they're orthogonal. In between, we do not impose orthogonality because we lack that assumption. That in contrast with the Laplacian approach. And the distance traversed by the vector field is more precise than the cortical distance, the depth map. So we represent the cortical ribbon mathematically as follows. We have a parameterized surface Q from U to R3, where U is the oriented 2D manifold. Now oriented because we want the inner surface to be projected upward, and Q is the smooth embedding, and for open surface U is the open subset or R2, and the orientation U provides through Q an orientation QU and a normal vector and Q. So in the next case, we say that the inner surface is the template and the outer surface is the target. And we create a smooth time-dependent vector field. Then with the diffeomorphic be just that, let it Q the time-dependent where Q1 is close to Q1U at the top of the surface, and BT is normal to Q, and you orientate the positive direction. And we are led with a constrained optimal control problem. We minimize the energy of the mapping with the velocity, with the regularization and the data attachment term, where the time at t equals naught, we have the Q dot 0, and the definition of the velocity, the differentiated of the diffeomorphism Q. And then we have the vector field QB normal, where the norm is defined by that. And N is the oriented unit norm of the Q at QT. And B is the R3 norm of the velocity. And D, the data attachment term, is the variable distance. It goes back to our assumption of the geometric properties of the plane. Now, in reality, the inner surface is a noisy triangulated surface, also the outer surface is a noisy triangulated surface. And so we have discrete measures of both the inner and the outer surface. We use variables with the mathematical framework coming from geometric measure theory, and it allows to define distances between discrete measures. And BQ, the regularization, is the combination of the extrinsic and intrinsic norm. And where S is the surface, evaluated surface. I will illustrate that in a moment. And the gradient S is the intrinsic gradient, and sigma S is the area form of the surface. And the velocity vector space B is the reproducible kernel Hilbert space on R3, whose norm ensures that the transform is diffeomorphic. And then, because we are working with an optimal control problem, we are working with constraint that the vector normal of the inner surface and we treat the outer surface orthogonally. That we use augmented Lagrangian to solve the control problem over with the triangulated surfaces, in which the normal vector computed by finite differences. This is the most computation intensive part of the algorithm. And the relevant parameter for computation, the data attachment term, the variable, uses a Gaussian kernel with 1 unit and with 100, and the deformated kernel, the Laplacian of order 3, and the width of 5 units would mainly be adjusted relative to the expected thickness and depth of the cortical area. So here are some typical computation we have done for the cat and the motor cortex in the human. the hearing baby and the deaf baby, deaf adult. It is from the vertices, you fall down the vertices for the deaf cat. And faces, if the faces, the M1 from a 17 scan, pulse by millimeter. Hearing baby, we upsample the data, so that's why these are small. The deaf adult one by one. The iteration, the one time quite high, but we have a lot of bases. But the bases can be quick at 1 hour. The one time it's affected by the number of bases could be Python project help. Here is an example of the M1 cortex. What we looked at was 3 subjects that was scanned 1 week apart, that we wanted to see our method could replicate the cortical technique. And that replicate is very important. It had a validation in the sense. So we took the motor cortex of 1 subject, and you can see the inner surface and the outer surface, and you see the thickness 3 millimeters on the top of the gyri, and about 1 to 2 millimeters here. And then 1 week later, we look at this, we do the same, we segmented the scan, and we generated the mapping, the similar, and then and another view from M1 1 week apart. You can see the normal lines here. Likewise here. And then here here is an example of the evaluated surface. Actually go from the inner surface to the outer surface. And then for validation, what we did was we got the distribution of distances. You go from the inner surface to the outer surface. Week 1, and the distribution of distances from the surface from inner surface to the outer surface. The second week, and we can see that the little difference between the 2 CDF. So it sort of validates our method. Now we're going to apply this to the deaf brain. Since 1990, there have been 60 functional MRI studies of deafness, but they view structural study of deaf people. Unfortunately, the problem is that they focus on a homogeneous group. In other words, deaf people who use sign language, who do not use hearing for listening spoken language. But there are deaf adults who have been using auditory stimulation since birth, and they form a different and a heterogeneous group. Here, this example, the difference between 2 types of deaf people who use sign language and deaf people who don't use sign language. There is definitely a difference in the functional response and the auditory cortex. Actually, I participated in that study before I got my cochlear implant in 2011. At the University College London. Okay, so we look at deaf baby. Here's an example. The left hexagon will contain the primary cortex, and you can see that the deaf baby is about 9 months old, and it's pretty thick, and the hearing baby is somewhat thinner, and a better form, if you will. You could argue that. And so, the left heterozygous and the right heterozygous baby, 18, 19 months, deaf baby, and 16 and 26 babies. You can see that the continuous line is the normal hearing, and the dark line is the deaf baby. And the dark blue line, we pull them all together, and the dark red, the dark dash line, we pull all the deaf baby. Likewise for the right side. So there may be a structural functional difference between the left and right and the heterozygous, because the left is believed to be responsible for temporal processing of speech, and the right is believed to be responsible for frequency processing. But we are looking at babies who are still developing, and we know that between 0 and 3, the auditory cortex is still maturing. So but these are deaf babies who never use hearing aids because they've been diagnosed and they're waiting to get a cochlear implant, so they have a bit stimulated. Yeah.
Yeah.
Yes.
Yeah.
Yeah.
I don't really understand what you have on
Oh, sorry. These are
you
the
have distances, but you have two different populations.
two different populations. Yeah.
So this distances is
The distance of the length of those lines.
The thickness, like it's thickness. That's
Yeah.
Distance is thickness.
Of each line. Yeah. So that.
okay. This is okay. Because okay. I understand.
Okay.
So this is the width.
The width of the width. Yeah. All the point.
Okay. Oh yeah.
Okay.
Thank you.
So the dead baby is thicker than and they may not be, they may be the same at the right, but the which is more important is peace processing. There may be a significant effect of the lack of stimulus of the auditory cortex. Okay, the baby summary, we can calculate thickness, volume and surface area of the inner surface. And the significant P less than 0.05, one sided T test difference. I mean, different in me, only with the thickness. And then left and right, so left and right. So left has a dollar, right has a dollar. Now the depth of that, we see something similar. The hearing the planum temporal is the smooth. You have to be careful. We take it with a grain of salt because it's a small study, and close by. The big problem with MRI study is that many of those type of deaf people subsequently go on to get a cochlear implant, and you cannot put somebody with a cochlear implant in an MRI scanner. There's no other way unless you do it pre-operatively. And I would like to be able to get those scans before that, and maybe do a biomarker to predict the outcome of cochlear implant. So it's for the left heterodox and the left planum temporalis, and the right heterodox and the right planum temporalis. Now we have to take it with a grain of salt, but my interpretation is that the planum temporal responds to the language development and so forth. And all these deaf adults possess good language, spoken and listening language. But the left heterodox, they started using hearing aids from day number one, so they may have learned to listen with the hearing aid initially. For the right, they may have difficulty in processing frequency, repetitive sounds. But the primary important point is that for a few subjects, including me, who cochlear implant now, and we can talk on the phone. I can talk to my mother on the phone. After 5 years, I'm able to talk to my mother on the phone. Okay, so how do we compare our thicknesses with the most widely used software, free surfer, which everybody uses, and I don't use because I have some qualms about using free surfer. Every time you write a paper, people say, why don't you use free surfer? I say, okay, thanks. Free surfer is a hybrid half-stop distance. So fix the point VI, and you find the shortest point, which is FVI, and then you flip back and find the shortest point related to BJ, and you take the average of those two, and then you create a distribution. So increasing the distance would sort of underestimate of what the true thickness, in my opinion. And clearly you can see the free surfer is an underestimate of our thicknesses. Okay, for the deaf adult spouse doctor, take it with a grain of salt. We found that there's some significant right planum temporal for surface area and volume, and thickness is a trend. a twang for the Habad Tower. Now we're going to look at the deck cut, which is really at the heart of what we do. And this, in my opinion, is a very indicator of why we develop normal coordinates. You can see that the part of the deck, ordinary coordinate in the deck cut. You can see the diagram is quite thick, but the first side is thin, and that to be expected. And you can see the normal line representing what I believe to be cortical column. And then you can see expand the view of the diagram crown, and you can see this. And then the thunder of the cursor here. And I believe you cannot do that in other methods. It's very difficult to calculate these distances and the deeply buried cursor. And in the hair cut, you see the similar part. With the one cut and one hair, one deck cut and one hair cut. And here, the thing is that in the deck cut, you can see that it's pretty thick here and underdeveloped, not so deep. Here deep, but here not so deep. Well, in the hair cut, both are deeply buried in the hair cut, which means that the normal development. And I can demonstrate, quantify that difference. Here, the direct crown and the cursor here. So because also free surface underestimate the true thickness. And then here you can confirm that the deck cut is thicker than the hair cut. The two one cut, one deck cut, one hair cut. Okay, so the final step is we've now developed normal line. Now how do we define a mapping from the inner surface to the outer surface? Well, J be the volume of the surface evolution, and Js the disturbance of the surface, and B the normal vector field. And so we can define a normal volume, normalized volume, which by the evolution of the volume by the T from T where the inner surface to the outer surface is the proposed volume traversed by the trajectory at T. And the question we want to ask is, we would like to examine eventually whether they is constant cortical as claimed by Bock. Well, it's an open question. Bock hypothesis is Bock hypothesis true. Now, people are examining software called laminar Python to generate equivalent map of the cortex based on image data. We will now compare our surface evolution with the image data here. So the deck cut does involve the surface below the Bock equivalent hypothesis. Here we have the inner surface here, and then we have the outer surface, and then we have the evolution of the surface at T equals pulse 5. And then now we overlay that on top of the equivalent method of the software. We come to the relative depth, pulse 5, to match with our surface, but that is quite do that. At T equals pulse 3, you underestimate here, or possibly here, but not here, but it's too close to the pulse 5 line. Pulse 8, and the hair cut, the same similar thing, could be the difference here. There's also difference here. Yeah. And part 8. So we have a movie. I'll show the movie in this. I already generated that last week. We managed to get this working last week. And then the next one is the hair cut. Okay, so the visual work. Okay, we're looking at neurodegeneration, neurodevelopment study. For example, atrophy in the entorhinal cortex, the eye damage disease, the PhD student of our school classes. And then now, in order to be able to validate Box hypothesis, we have post-mortem data, we have the histological section, and we have the 3D brain. Then we can map the histological information, we define the cortical layer 1 to 6, and we can transfer that information to the 3D space. And now we can see how the cortical layer can be interpreted in terms of the evolving surface. So we're working on that next. So for that to happen, we will have automated segmentation initial HMI section from cat to the inner and outer curve of cortical layer. And then we add the amendment to map the sparsely sample curve to high resolution surface template to transfer the histological data to 3D space. And ultimately, what the German want to do is to be able to correlate, have a 3D correlation between electrical activity in the brain. For example, we will have two electrodes, and we will have a recording electrode. Unless there's a secondary audio cortex, and we will go to the upper layer, we go down to the lower layer. At the same time, we stimulate the audio cortex in the primary, and we go from the upper layer to the lower layer, and we will have a 3D correlation. And that's why we want to build a 3D coordinate system of the cat to understand the effect of deafness on the brain, and body thickness and everything. And multiple part of
what are the physiological, functional implications of whether Box hypothesis is true or not?
Most what? Of the last part you said.
Whether the Box hypothesis
Box hypothesis
is true or not. What difference does it make?
Well, okay. What the question you want to ask, whether the layers are preserved, and you go from one area to another area, whether the body, the abnormal body, changes that preservation of the layer. So let me flip the question around. What are the physiological effects of abnormality, deprivation, of auditory deprivation? If we deprive the auditory cortex of sound, the brain will be abnormally folded. So we may be able to quantify that. And then, with the histological data, we would like to look at the cellular properties of the perimeter cells and so forth.
The optimal control problem you're solving, suppose you apply this, right now you apply to the inner layer to the outer layer to get one set of solution. Suppose the method is good, then in principle you can choose the intermediate layer and solve the same problem.
The mid layer.
And would you get the same velocity field?
The same
V.
B.
You're finding the vector field. So, in other words, what's the physical justification for that in relation to growth?
Well, the same B as what?
So maybe I have two questions. One is you solve this optimal control problem, which you define, is minimizing kinetic energy plus a D term, which I don't know what that D term is. So there's some reason for this, and then you get the coordinate system. That's right. So you you get the coordinate system
the velocity B
for two surfaces.
The velocity B is normalized.
Correct. So normal here.
But we look at the evolving time. Not the T equal naught where it starts at the inner surface, and T equal 1 where it starts at the outer surface.
But if I think about growth, this happens at every infinitesimal time step. So in other words, if I wait 1 day later, if I do the same problem, I will get a different set of coordinates versus I wait 2 weeks later, because the two boundary conditions are different. Because in the intermediate range right now, The coordinates, they are not
T
orthogonal.
is abstraction.
Huh?
T is abstraction.
Oh, I couldn't understand.
Not time. It's
Not time.
It's
But nevertheless, the question, so, in other
the
words,
mapping.
Just because there was a contradiction in the slide. The coordinates are orthogonal at each time.
yeah,
Yeah.
the coordinates at each time
At each time.
is
They are
orthogonal.
Yeah, all over.
So all the ones are orthogonal. So you at every time step delta t, you generate a set of orthogonal statements. So in other words, you do this minimization for infinitesimal delta t, and then you do that, repeat that.
Yeah, and so basically,
Yeah.
if you start from the, I think from t equal 1/2,
Yeah,
you will get the same thing.
right. So that's the answer.
Yeah.
Okay. If you do that for every time step, then.
From what I understand, you have a model which makes more sense from a generative point of view than let's say free surfer, which is just a naive projection. But do you have and your matching looks very good, but do you have a way with microscopy to check that the actual columns they follow more your model?
Yeah, actually, whether the normal line will be actually true biologically. But this is what I want to do next, because we have the opportunity, because I talked to somebody from the neuroscience department on Wednesday. Okay, so he told me we can look at the big brain data, the big brain, the high work through the brain from Germany. We cut a piece of that brain and do what we do in a cell and outer cell. And then we could transfer the histological section, for example, here. And we could see whether the line actually follow those lines, if they do that big biological validation of those lines. Yeah. Without else.
So in few years.
So why is the thickness is larger for that?
Oh, because the delta and the baby and baby.
It seems
In
that
the embryo-
you have to remove.
The baby, the embryo, you start with a binary synapses. At the auditory cortex begin to be activated stimulation. You don't necessarily use everything. You can throw out some of those cells, and the normal brain, the synaptogenesis become reduced over time. And the famous paper in 1997, which they show that the auditory cortex, then synapses, the density of the synapses rises and then falls off after 3 years. And so that makes the auditory cortex become thinner in normal baby than in deaf baby. In deaf baby, there's no stimulus, no stimulation, and there's no.
Yeah, but they could throw away everything.
No. The human, but there's no maybe a lack of a feedback system to tell the brain to prevent the brain from throwing that. The brain with the unused cell, it's there. It lack of stuff. Okay.
Other questions? Okay, in this case, let's go for lunch.